On to section 4.2, we're going to be discussing Newton's first law, and it states that no force acts on an object, or that when no force acts on an object, or when the vector sum of all forces acting on it is zero, the object is in equilibrium. If the object is initially at rest, it's going to remain at rest. If it's initially in motion, it continues to move with constant velocity. It's not accelerating. This law is valid only in inertial frames of reference. So we've got a situation here where we've got an object. We have a force pushing on it this way. We have a force pushing on it that's exactly the same magnitude, but opposite in direction. And let's say that that ball was moving with a constant velocity in this direction. Even though these forces act on it, it's still moving at a constant velocity. Okay, so here's a tutor demo that would be good for you to go and watch. Actually, there are several of these. So again, here's our discussion of Newton's first law. Every object continues either at rest or at a constant speed in a straight line unless it is forced to change by forces acting on it. So catapults are based on Newton's first law. When a catapult arm is released from the cocked position, it's going to accelerate rapidly, and it's going to carry the projectile with it. When the arm hits the crossbar, it comes to a sudden stop, but there's nothing on that projectile to force it to stop as well, so it's going to keep going. And once in flight, the projectile experiences no forward force. It flies on because objects in motion tend to stay in motion. It obviously does experience a downward force of gravity, and that's going to pull it down, but the object there is to hit a wall and hopefully break it open so that the opposing forces can get in. So it says here that everyday experience may seem to contradict this particular statement. So suppose you give a push to a hockey puck on a table. After you stop pushing and take your hand away, the puck does not continue to move indefinitely. It slows down and stops. To keep it moving, you have to keep pushing. And that is because as the puck continues to slide, the tabletop applies a frictional force to it in the direction that opposes the motion. So you've got your hockey puck here, you're pushing it and you let go. And according to what we've seen with Newton's first law, if there were no other forces that were acting on it to change its direction or acceleration, then it would continue to go. And that's not what we see. And the reason is that we have a friction force that is being applied to it to keep it from moving in this direction. Now, let's say we change the surface to ice. What we have done is we have reduced the friction force. We haven't eliminated it, but we have diminished that frictional force. So the puck is going to go further. However, its velocity will eventually come to rest. An air hockey table is probably the best case scenario that we have here on Earth for a situation like this. So we've got a puck that is being suspended by air. And as we push it and then let go, it will continue to go for quite a bit before it will come to rest, either by hitting the side of the object or depending on the net frictional force that's being applied to it. Inertia. The tendency of an object to remain at rest or to keep moving once it is set in motion results from a property called inertia. And that's what you feel when you're behind home plate and a fastball pitch hits your glove, and that baseball really wants to keep moving, but your hand is going to stop it. Well, hopefully you have a glove on it. The quantitative measure of inertia is the physical quantity called a mass, which we will discuss in the next section. So, when a single force acts on an object, it changes the object's state of motion. And an object that is initially at rest starts to move. If the object is initially moving, a force in the direction opposite that of the motion causes the object to slow down. So suppose a hockey puck rests on a horizontal surface with negligible friction, such as the hockey table. If the puck is initially at rest and a single horizontal force acts on it, guess what? That acceleration is going to start up there on that puck. So it's going to be put in motion. Now let's change things up. Let's say that we've got two players fighting for the same puck and they're pushing on it with force that is equal in magnitude but opposite in direction. That puck ain't going nowhere. The resultant here of adding the forces together is going to be 0. So there's going to be no acceleration given. And if you break it down to components, you will see that the x direction and the y direction resultant of forces is going to be 0. So in the discussions of relative velocity, we've stressed a concept called a frame of reference. And this also plays a central role in Newton's law of motion. Suppose you're sitting in an airplane and it accelerates down the runway during takeoff. You feel a force pushing on your back, but you don't start moving forward relative to the airplane. If you could stand in the aisle on roller skates, you would accelerate backward relative to the plane. In either case, it looks as though Newton's first law is not obeyed. Forward net force, but no acceleration, or 0 net force, and backward acceleration. So what's going on with that? So the point is that the plane accelerating with respect to the Earth is not a suitable frame of reference for Newton's first law. This law is valid in some reference frames, but not in others. A frame of reference in which Newton's first law is valid is called an inertial frame of reference. The Earth is approximately an inertial frame of reference, but the airplane is not. And this may sound as though there's only one inertial reference frame of reference in the whole universe. But if Newton's first law is obeyed in one particular reference frame, it is also valid in every other reference frame that moves with constant velocity relative to the first. All such frames are therefore inertial. For example, figure 4.9. We've got 3 frames of reference, that of a person standing beside the runway, and that of a truck driving at a constant speed in a straight line, and then that of an accelerating plane. The stationary person's frame of reference is inertial. The truck moves with constant velocity relative to the person, so its frame of reference is also inertial. In both of these frames, Newton's first law is obeyed. However, the plane, which is accelerating with respect to those observers, is a non-inertial reference frame. So there's no single inertial frame of reference that is preferred over all others for formulating Newton's laws. If one frame is inertial, then every other frame moving relative to it with constant velocity is also inertial. And that just simply means that the velocity is not changing. Velocity is constant. This person's velocity is constant as well. It just happens to be 0. So both the state of rest and the state of uniform motion with constant velocity can occur when the vector sum force is acting on the object is 0. Because Newton's first law can be used to define what we mean by an inertial reference frame, it's sometimes called the law of inertia.